This meeting is being recorded.
The next section in chapter 14 in the worksheet here shows us an example with a fast initial step. So we're first given here the overall reaction up top. Let me get my drawing tool out here. So once again, we're given our overall reaction here. And below, we're given the experimentally determined rate law. So if this is the rate law, we have to try to figure out how these steps in the proposed mechanism will give us this observed rate law. So we should note that termolecular processes are rare. That's because 3 molecules would have to have the right energy and orientation in order for this type of process to occur. So this suggests that we probably have a 2-step mechanism, again, because 3 molecules aligning the right way with the right energy at the right time is pretty rare. So we have this proposed mechanism given down here in 2 steps. So we see our first step now is the fast step. So we have that initial first step being fast, and then we have step 2 is our slow step. So this is our rate determining step in step 2 here. So at equilibrium, we know in step 1 here that both the forward and the reverse reaction will be happening at the same time at the same rate. So our first step implies that we reach equilibrium quickly. The overall reaction, the rate of the overall reaction rather, depends only on the slow step. So let's take a look at the rate law of the elementary step for step 2. That would look something like this. So we know that rate 2 or step 2 isn't the only concentrations, right, that will be required for our overall rate law. So because we have a reversible reaction reaching equilibrium on our fast step, and again, we note that the forward rate equals the reverse rate at that time, we can actually plug in and solve for the intermediate NOBr2. Because we know that an intermediate does not last very long, and it cannot be included, therefore, in our rate law. So let's take a look at the forward reaction. That will be K1 times the concentration of NO and Br2. And then we have our reverse rate. So that will be K to the -1 now. So the reciprocal or the inverse of that K. And then the concentration of NOBr2. So now that we have these happening at equal rates, we can rearrange this relationship over here and solve for NOBr2, since that's the intermediate that we want to replace in our elementary reaction rate law 2 here. So again, we're going to solve for NOBr2 by rearranging. So we're going to divide by K to the -1. So we get K1 over K to the -1 times NOBr2. And then we can take that and plug it back into our slow step equation here. So our overall rate will then equal our K, and then we're going to plug in for NOBr2. And that's going to be, well, we can write everything out here, but we can simplify all these Ks to be 1K, since this is just one reaction. And then we'll end up with this here, Br2, and then there was the other NO here. So we have to include that. So that is where we end up with the experimentally determined rate law that looks like this, where rate equals K times NO squared times Br2. And again, that was given at the start of this problem.